Welcome back to part 2 of Specimen Preparation, Chapter 5, Forensic Toxicology. Let's look now at liquid-liquid extraction. We're going to discuss solvent selection, adjustment of pH prior to extraction, and other factors. Solvent selection. Body fluids such as blood, urine, bile, or an aqueous tissue homogenate can be extracted directly with an organic solvent to obtain organic substances such as drugs. This is a direct method used by toxicology labs all over the world. Blood and urine can easily be partitioned with an organic solvent without protein precipitation. Table 1 on the next slide shows extraction-related properties of solvents that have been used in forensic toxicology. You can see solvent polarity is very important when selecting a solvent for extraction. All drugs today have some degree of polarity. Table 1 shows polarity in two ways. One, the solubility of water in that solvent. You note this right here, grams water per liter. And the second is the dielectric constant, this column. These two parameters tell us how effective a given solvent will be for a given analyte. For example, see the next slide that shows caffeine. In the upper reaction, you see caffeine. Drug interaction with solvents is illustrated with caffeine and chloroform. Here's chloroform, the solvent. And with, down in this panel B, phenol with diethyl ether. As illustrated in this slide, caffeine is more easily extracted by chloroform than by diethyl ether because caffeine accepts a hydrogen bond from a donor solvent like chloroform, but has no hydrogen atoms to donate to a solvent such as diethyl ether. But phenol does. As included in Table 1, it is logical to add an alcohol such as butanol to hexane and achieve hydrogen bonding in all cases, since alcohols can accept and donate hydrogen atoms for hydrogen bonding with drugs. Adjustment of pH prior to extraction. After a solvent is selected, then a buffer is added to convert any drugs present into non-ionic form so they will readily partition in the organic solvent. Carboxylic acids are fully protonated 2 pH units below their pKa's to keep them non-ionic. This includes the following drugs that contain a carboxylic acid group: salicylic acid, acetaminophenzoic acid, ibuprofen, ampicillin, tetrahydrocannabinol metabolites. Drugs can be classified according to pKa's and other parameters. Strong acids, for example, pKa's are from 1 to 5. Weak acids, pKa's from 5 to 9. Neutrals, no acidic or basic functional group, extractable at all pHs. Weak bases, neutral below pH 5 or 6. Strong bases are unionized from pH 7 and greater, and amphoteric bases that have both amine and phenolic groups. The primary purpose of adjusting the pH for extraction is to create non-salt forms of the drug so they will be partitioned into the organic solvent. Acidic drugs should have the pH adjusted 2 pH units below the pKa to produce 100% unionized forms. Of course, we can predict this from Henderson-Hasselbalch equation. Yields of bases and acids are not improved by excessive adjustment of pH. That is, when 2 normal sodium hydroxide is used when 0.1 normal will do, or using 6 normal sulfuric acid where 0.1 normal will do just fine for the extraction. Neutral drugs extract at all pH values between 0 and 14, since the molecules are unionized at all pH points. The neutral fraction is difficult to analyze because glycerides, cholesterol, and cholesterol esters are recovered at the same time. The acid fraction is also contaminated with fatty acids, so removing of acids and neutrals prior to recovery of basic drugs results in a cleaner fraction. Let's take a look at figure 3. This is a fractionation scheme for the separation of organic drug substances according to acidity and alkalinity. This figure shows a separation of chemical drug groups by sequential extraction technique often applied to urine, a protein-free filtrate of liver, or to gastric contents when a general screening for drugs is needed. Aqueous fractions can be examined by UV spectrophotometry and immunoassay. Organic fractions can be examined by chromatography techniques such as GC, HPLC, and TLC. The aqueous fractions are re-extracted into an organic solvent to obtain concentrated extracts that can be chromatographed. And you can see the sequence here of a specimen being in an organic aqueous phase, and again separation, organic aqueous on both sides. Here's figure 4. 4 chemical classes of drugs exist. The dissociation constants as pKa's are provided. These are examples of the different drug groups. First up here is strongly acidic drugs such as salicylic acid. The next is weakly acidic drugs such as acetaminophen. And then this third group is amphoteric basic drugs, which are capable of functioning either as an acid or as a base, although they're weakly basic. And then 4 strongly basic drugs such as amphetamine. Other factors: some drugs that are hydrochloride salts are solvent soluble, particularly in chloroform, 1-chlorobutane and dichloromethane. Some high molecular weight drugs such as thiioridazine form hydrochloride salts that are solvent soluble. Other considerations with liquid-liquid extractions include cost, odor, safety. For example, diethyl ether has an unpleasant odor, high volatility, and flammability. It forms peroxides that will react with drugs. Benzene is a confirmed human carcinogen. Chloroform is a suspected carcinogen. So there are disadvantages because of these safety and cost and odor factors. Here's table 2. To appreciate drug distributions between a primarily aqueous phase and the organic phase, this table indicates recoveries of polar and nonpolar drugs using 8 different solvents across the top here. Notice that drugs with one functional group, such as a tertiary amine, are recovered in high yield by nearly all solvents. Polar drugs, such as hydrochlorothiazide, morphine, and caffeine, need more polar solvents. So this is a pretty interesting table to look at as far as solvent selection. Back extraction techniques is next. To get at least 70% recovery in the very beginning, the ratio of solvent to blood should be 5:1 or even 10:1. Even with using a lot of solvent, the initial extraction of blood, urine, or bile with organic solvent is the poorest yield step of all. Another approach to acidic and basic drugs is to recover them by back extraction into aqueous solution. In this case, there is a reduction in volume of the specimen for further concentrating and miniaturizing the procedure. One-step extractions can yield high recovery but can also not be very selective, since neutral substances are always present in one-step extractions. For chromatography techniques, it is best to use 3-step extraction: extraction, back extraction, and then re-extraction. Solid phase extraction is next on our list. This is an outline of the topics we're going to touch on here. Solid phase extraction was developed due to the drawbacks of liquid-liquid extraction techniques. These methods allow for the isolation and purification of fractions containing drugs and their metabolites. In-house columns. These were developed by toxicologists in the 1960s and 1970s. They were first columns of sodium sulfate to just absorb water. Then toxicologists started using shredded filter paper or cotton balls to trap drugs. Blood would be poured into the column first, followed by a solvent to recover the drugs. Following this, toxicologists started using other materials such as diatomaceous earth, a sedimentary rock of marine or lacustrine deposition composed mainly of silicon dioxide. These materials were loosely packed in columns. An example of column chromatography is the use of fluorosil, this term right there, magnesium silicate, packed into glass pipettes or Pasteur pipettes to recover organochlorine pesticides, DDT. After the drugs are absorbed into fluorosil, non-polar solvents such as petroleum ether or hexane are used to recover the organochlorine pesticides. Charcoal, activated carbon, is used in some columns by toxicologists. Commercial preparatory columns, beginning in the mid-1970s, chromatography supply companies started offering manufactured columns of various phases and types and purified packing materials to place into tubular glass or plastic columns. Materials included ion exchange resins, XAD resins, and purified silica gel. Silica gel comes from sand, which is 60% by weight silicon dioxide. Silica is sized, sorted to uniform shapes, and then used in HPLC, TLC, and preparatory columns. On-off columns is next on our list. Short, very absorbent, fast flow columns have been developed that 1. Selectively bind drugs from an aqueous matrix, 2. Allow carbohydrates, proteins, and polar lipids to pass through, and 3. Allow elution of the drugs with effluent solvents. The idea is to put the drug on the column in a few minutes, remove unwanted components, and recover the drug in a few milliliters of the solvent, and as a result, highly concentrate the drug. Appeal of solid phase extraction is reproducibility, batch processing, and minimizing the use of solvents. Bonded silica sorbents. Along with in-house columns, commercial preparatory columns, and on-off columns, bonded silica sorbents are another form of solid phase extraction. Hydrocarbon chains C8, C18, phenyl groups, polar groups, and an anion-cation exchange sites can be covalently bonded to silica and silica hydroxide on the silica sorbent. Isolation techniques are designed based upon a drug's functional groups, their hydrocarbon content, their acid-base groups, and their general water solubility. And not to be left out, there are 2 more. Solid phase microextraction. SPME is a newer technique being applied to alcohol and drug analysis. And the last one is esoteric isolation techniques. Since esoteric isolation techniques such as microwave extractions, Soxhlet extractions, countercurrent distributions, steam distillations, vacuum distillations, and Stas-Otto procedures are beyond the scope of this chapter. There is not now or ever one standard approach to isolating all potential analytes from biological mixtures. So we've really touched on a lot of them here. And that completes our discussion of specimen preparation.